Hey everyone, so we are living through this just incredible moment for AI, right? Breakthroughs are happening, it feels like every single day. But have you ever just stopped and asked yourself, if AI is getting so unbelievably powerful, why isn't our economy just taking off like a rocket ship? Well, that is the huge paradox we are going to unpack today.
I mean, it is the multi-trillion-dollar question, isn't it? We've got these AI models that can do superhuman things. They're writing code, they're designing molecules, they're completely changing whole industries. So why does the overall economic growth chart still feel kind of flat? What is getting lost in translation here?
You know, this really gets to the heart of it. There's this fundamental disconnect between the digital promise of AI and our physical economic reality. The paper we're looking at today calls it the information to reality translation speed gap. It's a bit of a mouthful, but it makes sense. It's one thing to have a breakthrough in the world of bits and algorithms, but it is a whole other thing to translate that into real progress in the world of atoms.
And here you can see that gap perfectly visualized. That one curve shooting up, that's AI capability in the information space, and it's growing at this dizzying exponential rate. But that other flatter curve, that's the real economy. The world of factories, infrastructure, and regulations, and it's just chugging along at a much slower, more linear pace. The whole puzzle is figuring out what's causing that massive space between them.
Okay, so here's the good news. A new economic growth framework gives us a really powerful way to understand and even to quantify this gap. It gives us a clear model for diagnosing exactly what's holding us back, and more importantly, how we can finally unleash AI's true economic potential. All right, let's dive in. So this new model starts with something it calls potential growth. Think of this as the absolute theoretical maximum power of our entire AI ecosystem. We're talking all the algorithms, all the research, and every single chip of installed computing power. The best way to picture it, it's the raw horsepower of a brand new, top-of-the-line supercar engine. Just pure untapped potential. But then you've got realized growth. And this isn't some theoretical number. This is the actual measurable progress we can see and feel in our real economy. So it's not the engine's horsepower rating on a spec sheet, it's the car's actual speed out on the road. And we all know a powerful engine is only one piece of the puzzle when it comes to making a car go fast.
And here it is. This is the crucial insight from the whole model. Our realized growth isn't just about how much potential growth we have. All that potential has to fight its way through two critical bottlenecks, a physical channel and an institutional channel. You can think of these like two big funnels that determine how much of that raw engine power actually makes it to the wheels.
All right, so let's break down that first bottleneck, the physical channel. In our car analogy, this is basically the transmission.
So the physical channel, it measures the gap between the computing power we've installed and the computing power we can actually deploy. It's like you can have the most powerful engine in the world, but if your transmission is clunky or inefficient, that power is never going to reach the wheels. This channel is the hard, physical reality check on all our digital ambitions. And what's so fascinating here is just how tangible and, well, physical these constraints are. This isn't some abstract economic theory. We're talking about the hard stuff. Can our power grids actually handle the insane energy demands of all these new data centers? Do we have enough fiber optic cable in the ground? Can we get the raw materials, the water for cooling, and maybe most importantly, can we get the permits and actually build this stuff fast enough? These are the real-world gears in our economic transmission.
Okay, so we've got our engine and we've got our transmission. But of course, a car also needs a road to drive on. And that brings us to the second major bottleneck, the institutional one. The institutional channel represents all the societal, human factors that either help or hinder AI's deployment. You could have the most perfect car with a flawless transmission, but if you're trying to drive it on a road that's just full of potholes, endless red lights, and traffic jams, well, you're not getting anywhere fast. This channel is all about the quality of that road.
And what determines those road conditions? Well, it's stuff like this. Does the public actually trust and accept AI? Are our laws and regulations even remotely keeping pace with the tech? Are companies actually ready to change how they do things to take advantage of these new tools? And does our workforce have the skills to even operate in this new world? These are the human challenges that can slow progress down to an absolute crawl.
So once you understand this two-bottleneck framework, it becomes incredibly powerful. Because we can move from just wondering why growth is so slow to having a clear, actionable playbook for how to finally unlock it. In this slide really frames the core choice we all face. The easy but ultimately wrong strategy is to just focus on building a bigger engine, pouring every single resource into making AI models more and more powerful.
The smart strategy, the one this model points to, is a balanced approach. Yeah, you keep innovating on the engine, but you simultaneously invest in upgrading the transmission and paving the road.
And this gets to the real danger of that lopsided strategy. Because just dropping a bigger, more powerful engine into a car with a weak transmission and then trying to drive it on a terrible road, that isn't just ineffective, it is actively dangerous. You could put so much stress on the system that you just break the car.
The research actually gives this a name, the overbuild penalty. And this is a profoundly important and honestly a pretty counterintuitive idea. The model shows that if you only invest in more raw compute power, the engine, without improving the physical infrastructure that makes it usable, you can actually reduce your real economic growth. You create this massive mismatch, making the whole system less efficient and, believe it or not, effectively lowering your top speed.
So what does this playbook actually recommend we do? Well, it sets out a really clear priority. First, and most urgently, we have to tackle the physical bottlenecks. We need to find the absolute weakest link in our transmission, whether that's the power grid or the permitting process, and fix it. Then, we can work on tuning the institutional channels, smoothing that road by building public trust, updating our regulations, and getting our workforce ready.
All right, so let's sum this all up. First takeaway, potential AI power is not the same thing as real-world economic growth. Second, that growth is choked by two major bottlenecks, our physical transmission and our institutional road conditions. Third, and this one is so important, just building a bigger engine can actually backfire, leading to that overbuild penalty, which means, finally, that the smartest path forward is the balanced one. Yeah, upgrade the engine, but you have to fix the transmission and pave the road at the same time.
And that really brings us to a final thought here. The journey to unlock AI's potential, it's less like a software sprint and a lot more like a massive construction project. It requires pouring concrete and laying fiber just as much as it requires writing code. So the question I'll leave you with is this. Looking through this lens, what's the single biggest physical or institutional roadblock you see in your world? Thanks for joining me.